Yes, thanks for giving this opportunity to speak. And so I wanted to say a few words about forward modeling, and I realized that in 9 minutes I cannot give a full review of that, obviously. So my apologies if there are some names I don't mention here, but I rather wanted to raise a few questions. So probably I will raise more questions and answer questions. But when I started thinking about this topic, then I was myself a bit unsure what exactly we know. So maybe the first point I want to make is that forward modeling of the host star atmospheres is a very important tool, not only for interpreting observation data, but also for developing and optimizing observation strategies. That also means fully accounting for instrumental effects. So questions that I came up with then was how detailed do we actually need to know the properties of the light that's emitted by the host star? That also means how detailed do we need to know the properties of the stellar atmosphere? And how detailed do we need to model the actual transit? Do we need to model everything at the same time? That means the host star atmosphere and the planet while transiting. Or do we get away with a more like a patchy statistical approach of that? That's something I would like to understand better. And if you see this illustration here, I just grabbed this rather randomly from the literature. The way you model the host star is the level of detail is very different, right? And the question is, how much do we have to do actually? When talking about stellar atmospheres, then quite often this relies still on 1D stellar atmospheres. And that brought me to some memory I have. My PhD supervisor was in the late 60s, early 70s, working on 1D models of the sun, empirical models. And his supervisor asked him one day, Hartmut, how much longer would you need to work on these models? So in the 1970s, that was apparently the notion that this should be detailed enough now, right? That we can move forward. 50 years on, I think we are still not there. So because what happened, obviously, is that we have seen some enormous progress in instrumentation for solar observations for the last decades, so that we know we get more and more data, we see more and more dynamics and phenomena going on, very small spatial scales, and the models need to catch up and explain all of that. So you see here the movie, which is not moving on the left side, is also very dynamic from a 1 meter telescope, ground-based, and of course on the right-hand side you see the solar dynamics observatory data. So we know today that the sun is a very dynamic object, and the next generation of solar telescopes, you see in the lower left, the decast 4 meter telescope, which might be followed by the European 4 meter telescope in the future. They will probably push this limit even further. That means we will see even more details in the future. So the models, as said, need to catch up with that. And the current state basically is that you have a self-driven, that means convection is developing by its own, time-dependent 3D MHD models with relative transfer. That is like what we have, the standard tool. And the next step we're seeing right now is the further development beyond ideal MHD. That means you take into account non-equilibrium effects. Hydrogen ionization is very important. There are first simulations with multi-fluid, multi-species methods, where you account for ion-neutral interactions. You will combine this with particle and cell simulations for flares especially, or even in some cases with chemistry for molecules. This is where we're going right now. The challenge here is that you have a large range of spatial scales and temporal scales that are important, that you want to capture, and especially the surface layers where our observables are formed that we need, they need high resolution. So this is, well, obviously what you would like to have is a simulation of the whole star that resolves the surface layers where the observables are formed sufficiently. That, of course, would mean an enormous number of grid cells and computationally completely prohibitive. So what one usually does is one is doing either global simulations, where you often just completely omit the surface layers, or you go for local simulations of the surface near layers or the stellar atmosphere. Just an illustration of how this can look like. On the left hand, we have global simulations. On the right hand, you have local simulations. And you see this is very different. Some codes can do both, but you really have to decide what you want to do in this moment. The problem here is, as I said, for the global simulation, you usually have to neglect the atmosphere, which makes it difficult to compare to observations. With the local setup, you need to select your activity levels. So it means quiet sun or plage or active region. You really have to decide. That means you need to make many different models for different types of regions and also for the different types of course. Nonetheless, I mean, what limits this obviously is the computational demands. And the illustration below here is from a Bifrost simulation with about 500 cube grid cells, and just 1 hour of solar simulation time. Then it would be 2.5 million CPU hours, right? And this is not standard anymore. So we have moved further, and so this means this is really costly. Nonetheless, high resolution is important, and you see this illustration here, 4 different snapshots from simulations of different resolution, numerical resolution. As you go to the lower right, you see high resolution is necessary to capture all the properties of the granulation and the dynamics that are going on. Another example from the Cobalt code. You see the dynamics here. This is a granulation intensity you see here. What is important here to conclude is small scales are really important, and the high resolution observations that can be compared to simulations make the sun an essential test case here. The SUNSPOT models, there are some first attempts, but still very challenging. I'm not going into detail on this. This is really at the frontier of what can be done. And another last important point I want to make maybe is that if you want realistic disintegrated stellar spectra, then based on the models, then what you can do is you take your 3D model, you make relative transfer, you get observable, spatially resolved. Here you see an example from NROV simulation for the Kelton 2K line. And if you want to go then to the stellar signal for that, disintegrated, you can either go doing the relative transfer for all spatial positions, then you average the observable, or you average the model first, you get like a 1D certification and do the relative transfer afterwards. And obviously this is not the same thing. In this particular example that's published in 2013, that would mean if you just go with a 1D model, you actually would lose the emission peak in the line curve of this line that you would clearly see in the 3D case. Conclusion here is the modeling in 3D is really important, although it's very costly. Some hope here, the whole SUN project, which started like 2 years ago as an ESC synergy grant, which attempts to couple now global and local simulations. Right. This is at the beginning, and it's computationally really challenging, and that probably will not be a standard tool anytime soon. But I think this is like highlighting where these models can go in the future. So, conclusion: you can't have it all yet. That brings me to my last slide here. So I just want to conclude with the questions here. So, what exactly do we need for numerical simulation of stellar atmospheres? Which scales do we need to resolve for actually modeling transits and for modeling the host atmosphere correctly? And can we get away with a statistical approach, or do we need to have realistic models that capture everything? So I would like to spark off a discussion here that defines the requirements that we have from such simulations. Thank you.
Thank you, Sven.
There's still music playing.
Yeah, I mean, I don't know where it's coming from.
It seems to be coming from you, Sven.
From me? No.
Yeah. Like if I mute you,
yeah,
we've stopped it. And again.
Well, you don't seem to be able to unmute Sven now.
Whoops.
Okay. Sorry.
Yeah. Yeah, so currently I don't see any questions in Slido for you, Sven, but maybe I missed them. But I was wondering, have you done any comparison to observations? Maybe I missed that if you said it, but I mean, like stellar observations, for example.
Not for the stellar case, really. We're working on that as well. But I think for developing the models, of course, the solar case is the best test case. But then it's always the question, how much of it can you actually transfer to other stellar types?
Yeah. Okay, thank you, Sven.